welcome to our presentation today. We are thrilled to have you all with us. My name is Catherine Nellis. I'm Assistant Vice President for Development with the university, and I've had the pleasure of working with a group of faculty who are presenting today on exploration of Mars. And I'm thrilled to introduce Jim Russell. He is Royce Family Professor of Teaching Excellence. He is also a professor and as well as the chair of the Department of Earth, Environmental and Planetary Sciences. I'll turn it over to you, Jim.
Thanks, Catherine. And thanks to everybody for coming today to learn about some of the great research that happens at Brown University, exploring Mars and other planets in our solar system. As Catherine mentioned, my name is Jim Russell. I'm chair of the Department of Earth, Environmental and Planetary Sciences. I'm just going to give a few kind of quick notes about the kinds of research, teaching, training, and outreach opportunities we have around planetary sciences at Brown, and then turn it over to a number of planetary scientists in my department who are actively engaged exploring Mars. So planetary research is really one of the crowns or the jewels in Brown's crown. We've led exploration of the solar system for more than 50 years. Our research history of exploring the solar system goes back to the Apollo missions, which were some of the first missions to explore the moon. The Viking lander mission in 1976 was led by a Brown professor, Tim Much. And this mission actually landed a lander on the moon and took some of the first on Mars, and took some of the first photographs of the Martian surface. Current Brown faculty have continued this really strong tradition. The Mars Reconnaissance Orbiter was one of the investigators on that, is on the call today, Jack Mustard. This mapped out the geological composition of the Martian surface. And we'll continue our strong tradition of leadership with the Perseverance Rover, which is going to land on the Martian surface in 2 days, 23 hours, and about 53 minutes. So coming right up. You're going to get to hear lots of cool work about the reconnaissance orbiter rovers that are currently on the Martian surface that are actually being steered by Brown faculty, as well as the kinds of things that we hope to be able to learn from the new Perseverance rover. Our planetary group has been it's a big and diverse team of scientists, students, professors, researchers. And the three people that we've brought today have really embodied the tradition of excellence in research and teaching at Brown. Professor Ralph Milliken is a member of our department and planetary group. He's engaged with the Curiosity rover that's currently investigating the Mars surface. Melly Meyer is as a graduate student in our department, also involved in the Curiosity rover. And then Jack Mustard, who I mentioned before, has led teams associated with the reconnaissance orbiter mapping Mars, and has led a variety of NASA panels to try to sort of map out how the science community investigates the Mars surface. Now, this team for decades has been housed in the Lincoln Field building, and I know we have a few alums on the call. Many of you will have very fond memories of the Lincoln Field building. But the Lincoln Field building, we're about to undergo a major renovation of Lincoln Field. The planetary science research, teaching, education, outreach, all of this is changing, and we really need to refurbish Lincoln Field to continue Brown's excellent leadership going forward into the coming decades. And so we're really looking forward to the kinds of opportunities that we will have in a renovated Lincoln Field. Just to kind of put a picture on that, we're going to completely convert the interior of Lincoln Field to kind of showcase all of the really outstanding research that happens at Brown in planetary science, and to provide new opportunities to students, faculty, and researchers investigating planetary science at Brown. So with that, I'm going to turn it over to Jack, who's going to talk a bit, not Jack. With that, I'm going to turn it over to Melly, who's going to talk a bit about the ongoing research that she's doing on Mars.
All right, hopefully everybody can see my screen. So I'm Ralph Milliken, professor of geological sciences here at Brown, and one of my areas of expertise and really my passion and fascination is with planetary science. And we'll also be able to hear from Melly, Meyer, a graduate student working in my group on the Curiosity rover in just a little bit. So this may look like an image of the southwestern US, but it is not. It is a false color enhanced image of the surface of Mars. The sky on Mars is not in fact blue as you see here. It is a reddish brownish dusty color, but this really just highlights the diversity and the rich history of rocks and the geologic record that we have on Mars to explore. And I'll talk a little bit now about what we have been doing with the rover on the ground with the Curiosity rover for the past 8 years now. We landed in August 2012. We've spent over 3,000 days on the surface of Mars in a place called Gale Crater, and we've learned an awful lot. And this really has set the stage for what the next great rover is going to do, and that's the Perseverance rover, which is set to land next week. So many of you may be familiar that we have a number of different missions that have gone to Mars, mapped it from orbit, as well as explored it in situ. And this rover, it's one of its primary goals is to understand the biological potential of Mars. And in fact, there are actually 4 high-level mission goals from NASA. Assess the biological potential, understand the geology, geochemistry, understand the role of water, and water is needed for all life as we know it, so that's a critical component. And also thinking forward to the future in human exploration, we really need to know something about the surface radiation environment and the risks that that might pose to the future men and women who will explore the surface of Mars. Now, one thing I do want to note, though, this is not so much a life detection mission. For all the great things that this rover can do, there are a lot of things it can't do. As an example, if you had microbes living on the surface of Mars today, we really wouldn't be able to tell that they were alive. And this has to do with the kind of instruments that we are limited to using with this type of exploration, but that we'll talk a little bit more about that later, and thinking forward to why it's so important to get samples from Mars and return them to Earth. So this is just a map showing kind of where we've been with various Mars missions, the US and other countries as well. I'll note the white arrow is highlighting the location of the Curiosity rover. The black arrow is where the Mars 2020 Perseverance rover that's landing next week is going to go. This is a topographic map where red, brown, white colors represent high elevations. The blue kind of purple tones represent lower elevations. And you'll see it's quite a diverse planet. Now, what's really interesting about Mars, I think, from an exploration spacecraft point of view is it's really, really hard to land there. It's more than half of the missions fail. It's extremely complicated. The atmosphere is just thin enough that it doesn't really provide you with a lot of cushion when you're jetting in and trying to land safely, but it's thick enough that you really do need to worry about it so you don't burn your spacecraft up. So Mars, it's really tough to get there. So where did we actually go in detail with this Curiosity rover? Where have we been exploring? It's this place called Gale Crater. It's about 150 kilometers in diameter, absolutely enormous impact crater that formed about 3.5 billion years ago. So that's just for perspective, that is older than nearly all of the rocks on our planet. We have plate tectonics that recycles the crust of our planet. Mars doesn't seem to have ever had plate tectonics. So it really has this very long, billions of years history preserved at the surface that we can explore. And within this crater is this 5-kilometer tall mountain that we call Mount Sharp. And that mountain that you see in the middle here, that was formed after the crater and impact event. And what we've seen from our reconnaissance orbiting data is that the rocks in this mountain are stacked pretty well on top of one another. So marching from the bottom to the top, we're marching through geologic time. And there's a lot of water-bearing minerals in this mountain. And those water-bearing minerals are different from where you start at the bottom to going higher and higher and higher. And ultimately they disappear, it seems. And we're just left with the kind of dry, dusty materials that typify the surface of Mars. So this is one of my favorite images because it's one of the first ones we took after landing back in August of 2012. This is taken with like a 100mm kind of camera lens that we have on the rover on the mast package. And so it's kind of zooming in. And it's really hard to get a perspective of the scale of this because there are no trees and shrubs. This is Mars after all. But if you look really closely, there's this tiny little speck in the center. That's about the size of the Curiosity rover. So I always like to say that is what we call job security. We're never going to run out of rocks to look at, and there's always going to be more to explore. And I will say, we're nowhere close to getting to that boulder yet, though we've gone quite a ways. So really just the highlights. What did we actually learn from this mission so far over the past 8 years? And what do we hope to gain over the coming months and years? And what does that mean for the new rover landing next week? Well, major finding number one, there was a lake in this crater over 3 billion years ago. All right, so over 3 billion years ago, we had water on the surface of Mars. It was long-lived enough that you actually had a sustained lake here. You were dumping sediment into that lake from rivers rushing down the sides of this crater. We don't know how deep that lake was. That's very difficult for us to assess with the kind of rocks we've seen so far, but we know it was there. And we've explored lots of different stones, particularly mudstones. These are very fine-grained rocks, the exact kind of rocks on Earth that are excellent at trapping and binding and preserving organic compounds. And so this is just one image of some of the vistas that we've seen. What we've also found, though, is the water in that lake was relatively benign. So you could have actually probably drank that water and been perfectly fine. And odds are you probably wouldn't have to worry about getting too sick because it doesn't seem like it was chock full of bacteria. That being said, we have found evidence for organic compounds, and these are not from terrestrial contamination in the rover. These are compounds that exist on Mars that we have discovered trapped in these ancient rocks. They're relatively simple compounds. We cannot say definitively that they were formed by life. I do want to be clear about that. They're carbon-hydrogen compounds. Some are chlorinated. So we don't know that this means there was life on Mars, but it's pointing us in the right direction, that we know you had all the raw ingredients you needed for life to have existed in this type of location. Specifically, we need 3 things. We need water. There's plenty of that. You need critical elements for all life as we know it. They call it the CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These rocks have all of those. And you need a source of energy. In this case, we've been able to demonstrate that there were different elements in reduced and oxidized forms. They were effectively chemical pathways that life could have used for metabolism. And again, that's not to say this did happen there, but all the right ingredients were there that you could take a lot of different types of microbes and bacteria on Earth. You could drop them in this environment and they would have been perfectly happy. But we also see that this lake was drying out at some point in time. And there's evidence of this here in this example, which is showing you these kind of fracture patterns that you see. There's the ones that are filled in with white material. Those are calcium sulfate gypsum salts. But the other fractures that you see, these are what we interpret as mud cracks. So you have effectively wet, muddy stuff, just like in a puddle here on Earth. Rain stops, sun comes out, it dries up and it fractures and cracks. That's what you're seeing here. That's what we interpret this as. These muds have dried out. They've been exposed to the air. So that lake was getting shallower at some point in time. So how do we actually determine all of this, and kind of how can we say fairly confidently that this is what we call a habitable environment on Mars billions of years ago? Well, we do it by drilling. This is one of the big advances with this rover. For the very first time, we actually were able to drill into rocks on Mars. And we've done it a lot of times over the past 8 years. In fact, I believe we have 2 additional drill holes that are not shown in this kind of montage here. So we've done a lot of drilling on Mars as we've marched around, working our way up this giant mountain, this giant stack of rocks. And one of the things I really love about this kind of montage here is that we always think of Mars as the red planet, right? It's red, it's rusted out, it's been oxidized, it's dry. But when you actually look at a lot of the rocks we've drilled, they're not all red. There's a lot of rocks here that are greenish and bluish and grayish tints, yet they have water-bearing minerals and they have iron in them too. It's not that they're iron poor, but that iron hasn't been oxidized. And so Mars was a very, very different planet and a very different environment billions of years ago than what we see and what we think of it as today, whether we're looking through telescopes or orbiters. And this is why it's so important to get onto the ground and actually get in close contact with the rocks and explore them in detail. Now, I threw this in here just because it's fun. We also really, just in addition to taking images for scientific purposes, we love to take images to kind of really show the public and everybody out there what this rover is looking like as it sits on the surface of Mars so far away from us. So this is one of our more recent selfies, if you will, where we actually reach out the arm of the rover. We have a camera on there. We point it back and snap a bunch of pictures. This is actually a mosaic of dozens and dozens of pictures stitched together. And when we do this at high resolution, you could download the full thing online. You can zoom in and see the individual little bolts and screws on the rover. It's that high resolution. Definitely check it out if you're into this sort of thing. It still blows me away that we can do this. So here's what the rover looks like, more or less pretty recently on the surface of Mars. Getting a little dusty and dirty since landing day, but we're still doing really well. So now I'd really like to hand it over to, again, one of the graduate students we have in the program here at Deeps to give her perspective as to what it's like to be a student at Brown, being able to be involved in these types of projects.
Thanks, Ralph. Hi, yeah, like Ralph mentioned, I am a PhD student here at Brown, and having worked in oil and gas for about 5 years prior to coming to Brown, I wanted to speak a little bit about just kind of like what it's like being a student working on the rover team, and also just generally talk about the unique benefits of kind of being involved in space mission operations and rover mission operations as they relate to, you know, being a student and gaining skills that might be desirable for industry. Surprisingly, I found like several extremely transferable skills between being a geologist drilling wells in Texas to actually being a scientist, you know, roving around and drilling on Mars. And, you know, first and foremost, both of these jobs, kind of the essential is that you need to be able to work in a team that integrates both disciplines of science and engineering to solve problems at hand. So I'm going to demonstrate this with just two examples, one from Texas and one from Mars. So when I first worked in Texas, I noticed that there were some clear, distinct differences between the immediate goals of a geologist and of a drilling engineer. Drilling engineers, they want to drill the hole really quickly so that it's really cost efficient. They want to drill it straight so it's really easy to case. And they want to just kind of drill in whatever rock doesn't get the bit stuck. Whereas geologists, on the other hand, they want to move slowly enough so that they can really understand the rock, you know, see what changes are in these rocks, you know, as we drill through the layers. How did these rocks form? You know, how did the oil get into these rocks in the first place? Sometimes they can even convince the engineers to stop drilling for long enough to take a core sample so that we can take the subsurface rock, bring it up to the surface, and better answer these questions. And so with a rover team on Mars, we actually see the same type of interface between scientists and engineers. Take, for example, on the next slide, we see this great outcrop that Curiosity just recently photographed in Gale Crater along its traverse. So what do you think a geologist thinks when they look at this picture? Well, of course, they're going to want to drive closer. You know, they're going to want to get up and rove as close as possible to this outcrop so they can see the really cool sedimentary textures and really think about, you know, what environment shaped this rock over 3 billion years ago. So what do you think a drilling engineer or an engineer is going to want to think when they look at this picture? Well, they're immediately going to look at all of the loose rocks and the bunches of sand and say, wow, that's going to get our rover stuck in it. And they might even pull out a calculator and start to, you know, look at the angle of that slope and start to get nervous about how steep of a slope that is for the rover to get up when we want to go get up really close. And so my point being from these two stories is that whether you're on Texas drilling or you're on Mars kind of roving around, successful operations definitely draw on a balance between the opinions and desires of a diverse group of people. And I think coming to this realization as a student that no matter what field you want to work in, you're always going to be working with a diverse group of people. You're going to be leveraging a variety of expertise that expand further than your own. And you're going to need to learn how to clearly articulate your perspective, and you're definitely going to need to compromise. So mission involvement gives me as a student a direct experience to really kind of see these concepts play out in real life. And what I think is really cool about Brown is their Planetary group is that they have multiple professors and research associates and emeritus faculty that all have mission operations experience, instrument design experience, and are working on important related laboratory experiments that all relate to these types of questions. So I just feel really fortunate that I get to be here and really tag along with all these opportunities.
Great, thanks, Melly. And so as Melly noted, these are sandstones we're seeing in this image. And so when we think about the evolution of this location on Mars, we've been driving through actually hundreds of meters now of these water-rich kind of mudstones, or the water being in clay minerals and other kind of salts that we see. But we know it wasn't that way forever. We also recognize that at some point it all dried up. And in fact, Mars as a whole dried up. Surface waters are not stable. The low pressure, low temperatures. We have ice at the surface of Mars in a variety of locations, but liquid water is not stable. So what happened? What happened that Mars changed so fundamentally and so dramatically over several billion years ago? That's the big question for us. And of course, what does that actually mean for the prospects of life? Again, all life as we know it, you need water. So what does that mean if your availability of that critical ingredient was disappearing, maybe getting pushed deeper into the subsurface? And one of the reasons we chose Gale for a landing site, and why I and others were big advocates of this particular site, is because it seems to represent a microcosm of this global drying out, where we go from water-rich minerals and rocks at the bottom of the mountain to the absence of those things higher up. And so is it in fact a microcosm? And I just put this in here just to show you kind of some of the really high resolution images we can get. As a geologist, I like getting out my hand lens and looking up close at rocks and seeing them in detail. This is right now is the best we can do with the rover to kind of mimic that. This is a camera called Melly by Malin Space Science Systems that is kind of designed to mimic what a geologist's hand lens would do. And this is actually showing you some of the individual little sand grains within these sandstones in Mars. And in this case, they're mostly just crushed up basalt that's been kind of welded together. All right, so what's down the road for us? So I should say up the mountain, perhaps. The arrows kind of in the lower left is kind of indicating where we currently are. We're driving up this mountain slowly. We're approaching a fundamental transition in the rock record on Mars. And this is one of the reasons we went to Gale, because we've been exploring these rocks that are rich in clay minerals, great for trapping binding organics. But higher up, we are now getting to a region that we believe is saltier. It's filled with sulfate-bearing salts. So the green zone that you see is the kind of clay-rich materials. The yellow zone are these sulfate salt-rich materials. And we're just about to cross that transition. And so I and many of us on the team are super excited about this. This is kind of what it looks like, as we drive along, and those salty rocks are just ahead. What does this mean about the water of the chemistry of the water on Mars? Was it changing? The water that we saw before or interpreted in the rocks seems to have been fairly conducive to life, as I mentioned. But was it getting too salty for life? How is this changing at the surface of Mars? What does this, in fact, relate to the global kind of drying out of the planet? We don't know. These are all questions we're super excited to explore as the days, weeks, months, and years continue with this rover. And I'll just close by saying there's a lot of things that we can do with this rover, but we can't do everything. The rover stays there, the rocks stay there. And as a geologist, and kind of as Melly alluded to, boy, there's nothing we'd like more than to get our hands in those rocks and actually look at them up close. And that's something we cannot do with the Curiosity rover. We're always going to have more questions than answers, but it has positioned us extremely well to think about the next rover, the Perseverance rover that's going to Mars, landing next week. And so without further ado, I'll go ahead and hand things over to Jack to talk a little bit about that rover and what we can look forward to.
Great, thanks so much, Ralph. And let me just pass this over to here. Hey, it's really great to be with you all on the Zoom. Thanks for showing up. I mean, I know it's got a lot going on, but we're really excited to talk to you about this, what's happening this week. And as Perseverance begins this journey about seeking signs of life, and I just want to relate to you a little bit that I'm seeing more signs of life on the Brown campus these days as we get through this pandemic. I mean, it has been a really tough sled, but there's more students on campus and it's starting to feel a little more lively. So that's a positive sign. And hopefully it's a positive sign as Perseverance goes forward. So Mars has fueled our imagination for so many years, going back millennia, as the gods of war that we had with the Greeks and the Romans. But then with the emergence of telescopes, we actually began to be able to see it as a geologic object. And Percival Lowell, the great Percival Lowell, was fascinated by these linear features on the surface, and he imagined a planet with a dying civilization that moved as the water was transported on these canals. And that was fascinating, and it led to such great popular culture events such as the War of the Worlds, and now the movie The Martian, right? So gotta love Mars for bringing us all this. But it turned out that Mars was not populated by civilizations. The space age in the 60s brought us a very clear geologic picture of what was going on with this planet. Nevertheless, this was extremely Earth-like, right? So it continued to fuel the imagination about, could life have existed? Okay, so there's no civilizations here, but maybe life could have existed. And Ralph and Melly gave a really nice discussion of the kind of instrumentation and other things you need to get down deep and understand this. But nevertheless, despite all these fascinating Earth-like qualities, Mars had, after the Viking missions, which had life detection experiments that were found to be inconclusive or negative, the air went out of the room. People kind of fell silent on Mars as a high quality exploration target. Well, that changed in 1996 with a study of this rock here. This rock is ALH 8401, and the researchers studied this rock really intently. This rock comes from Mars. There's a meteorite found in Antarctica. It comes from Mars, and they found evidence that they said was from past life. Okay, this is a big deal. Past life, incredible. And it turns out that those 4 lines of evidence they had didn't hold water with the scrutiny of science, but nevertheless, it stimulated an incredible investment on NASA's part to go after this. Curiosity is one example of that, and the Perseverance Rover is our next example to really get at the science about whether or not life existed on this planet. I want to digress a little bit here and talk about Brown's footprint in planetary sciences and exploration. It is incredible. There's a lot of names on this. Up here in the upper left are just the names of the current people at Brown today who are doing planetary sciences. And the pictures you see on the right are some of the leaders we have in planetary science in the nation's interest who have Brown links, including Maria Zuber, who is chairing President Biden's Science Council of Advisors. She got her PhD in 86 and went on to a stellar career in planetary science, including leading missions around the moon. And then Ellen Stoffen in the upper left, upper right. Ellen was a contemporary of mine. We went to grad school together, along actually with Dave Crown, who I notice is on our call. We were in the Lincoln Field together, but Ellen today is the head of the National Air and Space Museum and has been involved in President Biden's transition team. So these are the leaders in science that come from here. Jim Garvin in the lower left is currently the chief scientist at the Goddard Space Flight Center. And then in the lower right is our next generation coming on. That's Bethany Ehlman, PhD 11, who's leading up a mission to the moon called Lunar Trailblazer, in addition to an incredible portfolio of science that she's developed related to Mars. And Bethany's deputy PI is actually another Brown graduate, Rachel Klima. So there's a legacy in there in an ongoing activity. And why is the footprint so strong? Well, there must be something about the secret sauce in Lincoln Field, and hopefully we can just not mess up with that too much as we go forward in the next generation. But I want to talk to you about the Perseverance Rover, and my role in that was to, first of all, chair this thing called a science definition team in 2013, which was 20 scientists who were brought together by NASA to say, what should this rover do? Ralph said, okay, look at what Curiosity can do. Curiosity was on the ground when we started this work. We had to say, what are we going to do next? And this had a series of science goals that were laid out determine whether life ever arose on Mars. And that's a pretty big science goal. And we knew we couldn't do that by one instrument, one measurement. We had to have a program and a plan. So the science definition team looked at that. And actually a key part of that is to return samples. Other science goals are to look at the geology and the climate, which are really important, much like Ralph and Melly are doing today with the Curiosity rover. And then this also was laying the groundwork for human exploration. It's actually to generate resources on the planet, which will cut the tether between the Earth and Mars. One of the things that our science definition team focused on was there's no silver bullet that we know of in science to be able to say, aha, there's definitively life using robotic tools. You've got to take a variety of observations. So there will be a test after this about this particular slide, whether you can remember the six measurements that the rover is going to make. But seriously, we realize we can do a lot on a planet. The ultimate way to go after this question is return the samples. So Perseverance will cache samples for eventual return to Earth. This is now the Perseverance rover, which looks a lot like Curiosity, and it does. It's not a carbon copy, but we were able to save money by using that. But it's got brand new instruments, and this is where they're all from. It's an international group of instruments, and they're going to be doing some of these measurements like here to get us further up that path to finding out whether life existed. Now, one of the sexier things about this rover is that we'll have its own helicopter. All right, so this is like can get from A to B. So it's going to be the first drone on another planet. And interestingly, this helicopter is carried in the belly, kind of off to the left here underneath. So it will be dropped on the first days as it lands. And then the team will spend about 30 Martian days to test drive the helicopter and then move on. But hey, this is going to be so fascinating. Can you actually drive a helicopter on another planet? So I want to now drive us towards why are we going to this place called Jezreel Crater? How do you get to this point? It begins with this phenomenal open competition, if you will. NASA puts out a call, says, hey, any place where you think we should send a rover on the planet? International call. These are 50 or more sites were brought together. We come together as a community. We discuss them. We rip it apart. We put it back together. And I want to say that and then we'd have another meeting in a couple of years later. And it's kind of like, voting people off the island. It whittles down on the basis of the community input until there's one. But as we got to the final meetings, there were 3 landing sites left. And they were, 2 of the landing sites left were brought forth by the Brown community in collaboration with the world, but the Brown community led them. And what we ended up with was the Jezreel Crater I'll talk about in a second. And I want to mention Jezreel Crater has this great Brown connection. The name of Jezreel Crater was proposed by someone named Caleb Fassett, got his PhD in 2008. And Caleb was working on this crater with Jim Head and said, this crater doesn't have a name. I think it's going to be important. So he proposed to the international community a name for this. And this name is meant to be, it means, the name actually means lake in Slavic languages. So it's kind of cool. So when you hear Jezreel, realize it's Slavic for lake. And Caleb Fassett, PhD at Brown, while he was at Brown, he made that connection. And I want to put Jesse Tarnas up there just to show our Brown connection again. Jesse just got his PhD last in September, and now he's working on the Perseverance rover. So we're continuing the legacy in there. Now, what are we going to see when we get to Jezreel? So this is the way Mars looks today. I mean, Ralph and Melly gave you better, like real images, but this is a graphic to explain. I'll show you the next one. This is what we think it was like 4 billion years ago, right? Whether or not that's true, this might be a little fanciful, but we need to go to the places where the water was and gather the rocks to bring home. And that's what we're trying to do. So Jezreel Crater, let me show you on the planet Mars itself. We have our polar caps up at the top. And then there's a big dark region called Syrtis Major, volcanic plateau. And then this little circle shows that the Jezreel Crater sits on the edge of the giant Isidis Basin, which will probably shape what we find. And then as we go now close right up to Jezreel, this is why everyone's so excited, because it has this beautiful inlet channel, and Caleb was one of the people who found this inlet channel and talked about it. And he also found that this had an outlet channel. So this crater filled up with water, and it formed this delta, which is the distribution of rocks here. And this is what it looks like in natural color. And what I'm going to show you is what it looks like in infrared color. And this next image was actually generated in the Lincoln Field building by Bethany Ellman when she was a PhD student. And you will see it every time people talk about Jezreel science. They will show this image and realize it came from Lincoln Field building. The colors here represent the exciting mineralogy. The green in particular is a type of mineral we call carbonate, like a limestone, even though it's not limestone. Okay, don't get me wrong, but it is a carbonate. And the rover is going to land right next to the front of this delta and start climbing up into this. So it's going to be a fascinating journey as it does this. So I'm going to move now to a little video of the landing. And this is the 7 minutes of terror that is talked about, because the spacecraft has to go from 20,000 miles per hour to 0 in 7 minutes. And it is an exciting journey. So let's see if we can follow that journey now right here. Okay, so February, this is coming up. This is a couple of days. I love the inspiring music. So coming in through the atmosphere, that's what it would look like. Here's the crater right in front of you. The parachute comes out and you get the first slowdown. So somehow we have to drop this rover. Where's the rover? Sorry, it comes down on a flying platform. And as it gets closer, it's going to hover and drop the rover on a tether. Is that cool or what? So I hope you guys can go live to this. It's coming up on Thursday. Put it on your calendar. We can all watch and see this happen. Oh, come on now. Okay, so it was really fun to give you this overview of the Mars rover and the Perseverance setup as how it got to this particular point in time. And now I'm going to pass the discussion over to Ralph, who's going to talk a little bit about how we're going to bring Lincoln Field back up to where it needs to be. Ralph.
Great, thanks, Jack. Okay, so I think hopefully everyone online is kind of getting a sense of just how exciting it is to be involved in these missions. And to me, this is just one of the great things about being at a place like Brown. There's such a long, rich history of exploration. And this, what I'm showing here, are kind of a bunch of the patches and logos just from some of the missions that folks at Brown and faculty and students have been involved in over the years, as Jim mentioned at the start. And again, they won't all even fit on one slide to be able to see them all. So exploration has really been central and key to the undergraduate, graduate program and all of the research and activities that we do. Of course, it's not just about the kind of, day-to-day operations of missions and things like this. It's also all about, again, reaching out with students and helping to train the next generation that will be the future explorers, the people who are going to design the instruments and come up with the creativity and the novel ideas for how to explore things within our planet and beyond, as we're talking about today. And so we have a really rich history of doing this, certainly with the undergraduates at Brown, and I suppose a number of you online might have even taken one of the classes in this. Professor Jim Head for many years taught a Geo5 class, introductory course in planetary geology. We continue to have these kind of courses that are quite popular in the department. And again, also looking forward to providing graduate students and undergraduate students with research opportunities in the Lincoln Field building, where all of these missions and these great activities have come out of. And so thinking forward, this is one of the things that I'm just really excited about, is that this opportunity we have in front of us to have a building that's revitalized, reinvigorated to really capture and display that excitement and enthusiasm that we have for exploration of Earth and beyond. And so these are just some of the kind of renderings from the design and architecture group as we think about what the new Lincoln Field is going to be like. We have a lot of different spaces within the Lincoln Field building now, and we will expand upon these in the future, that are related not only to teaching at the undergraduate and graduate levels, but also for outreach activities. The Rhode Island Space Grant is run through Brown with Professor Pete Schultz. We plan to have a full new kind of center devoted to that, with computational spaces where we can have groups from local schools come in, as well as teachers to do modules where we're training and working hand in hand with educators in the greater Providence region and Rhode Island region, so that we can work with them so that they can do further outreach and STEM education in groups, beyond the kind of campus of Brown, and then regional things as well, with bringing folks in from other universities, undergraduates and students, to give them opportunities. And of course, having excellent spaces that really highlight all the fun stuff that we do, and to have the research facilities and infrastructure to expand our footprint with the research that undergraduates and graduate students are able to do, so that we can ensure that we have a long, successful future, so that we can keep adding to all of those great mission patches that you see here in the decades to come, because there's a lot of stuff coming up, a lot of fantastic missions. Some of the things shown in here, it's not just NASA. We have partnerships with our colleagues in places such as the European Space Agency, Japan Space Agency, JAXA, as well as India, and work that was done in some of their missions. And so it's really an international effort. And I think everybody on the line here is super excited about what this new building is actually going to look like, and the great potential it has to make our footprint even larger and get that next generation and beyond. Really excited about all the opportunities out there in science and engineering as it relates to Earth and space exploration. So I'll go ahead and end there. I'm happy to answer any questions that anybody may have.
I can jump in. I see that some questions have already begun accumulating in the chat, and so I can ask a few of these. But if people would like to chime in, please go ahead and do so. Pose your question. But I can go ahead and ask some of the ones that have already appeared. So there's a question from Robert Sanchez that I think is an interesting one. So generally, why Mars? So we know there's water on Europa. In fact, we know there's water on a number of different planets. So why Mars in particular?
Yeah, it's kind of like, why not them all would be the great.
I would say that was my answer is, I would say, why not all of them?
It's the zero-sum game difficulty, right? I mean, the NASA budget is $20 billion, and you have to fit everything in there. And one of the reasons why Mars does show up again and again is because you can, every 2 years, you can go get a mission, get results, and plan for the next one. Europa takes a long time, and it's deadly to spacecraft to work around Europa. So Europa's coming up, but we need, like Ralph and I are saying, we need more targets, because it's going to be a great ride.
Yeah, I think it's a great question. All I'll add to that is there are a lot of places out there. I'm super excited about the Europa Clipper mission that is being developed and planned and built right now for launch in some years down the road, as well as other missions that are going to explore these kind of what are called ocean worlds, icy bodies that have liquid, oceans beneath their icy crusts. I think Mars does hold a special place, though, because as Jack mentioned, not only is it close to Earth, but the more we learn about it, and what fascinates me is it is so Earth-like in so many ways. And it prevents this rich history of sedimentary rocks. And when we look at our own planet, everything we know about life, or what we think we know about the origin of life on our planet and the explosion of life and the increase in complexity of life, comes from what is preserved in sedimentary rocks. So if nothing else, we know we have those types of rocks on Mars, and we can kind of use our Earth knowledge as kind of a blueprint as to how to go about exploring. Not that it's necessarily the best place to preserve it over billions of years, but at least we have a decent understanding from our Earth context of how to go about that problem of searching for the needle in a haystack.
But let me just continue on, because this is a good dialogue that Ralph and I can have, because I would say Mars is Earth-like, but it is not Earth-like, right? It's small, actually. It has not been as geologically active over its time. Its orbit is really messy because it doesn't have a big moon like we have. So it's great to think about it as Earth-like, but it's not the Earth. And as we think about these exoplanets that are going to be coming, it's like, how can we develop really a good framework for this exploration?
I also see there's another question in the chat about international cooperation as it relates with the UAE and China's orbiter. There definitely is international cooperation. I think in Jack, one of the slides that you showed had all the different flags for the different countries that are involved on the Perseverance rover. And likewise with Curiosity, there are international partners on there that have contributed instruments, scientific expertise, and these really are international ventures. And I think especially when we think about getting those rock samples from Mars back to Earth, that has to be an international partnership, and it will be, because quite frankly, I think it's just too expensive and complex for one nation to kind of carry all of that on their own. And science, it doesn't see borders like this when it comes to space exploration. And so I think, we're just going to see more and more of that international cooperation is my hope.
Yeah, and I think that, as Ralph said, getting the samples back from Mars, there is a plan in place actually with the European Union, the European Space Agency, and NASA already have developed a partnership. They're working out what they call the interfaces about how to make this work. So that's going to be an amazing 3-mission activity, bring them home. But that, as Ralph said, it can't happen without international cooperation. And
Another question in the chat from Thor Johnson is asking a similar question to the first one. So how does the moon compare to Mars for scientific and economic interests?
Mm-hmm.
Yeah, that's a fantastic question. I think my personal opinion is I'm very big and excited about sending humans back to the surface of the moon. I personally, there are a lot of different thoughts out there, but I feel like that is the natural first step to sending humans beyond into deeper space to places like Mars. I think in terms of the economic side of it, that's definitely something that folks like myself and others at Brown have been very interested in. A lot of the big thing over the past 10 or 15 years has been this discovery of water on the moon. Now, it's not a lot of water, but there is water there, OH and H2O molecules. And this is actually the focus of that kind of lunar trailblazer mission that Jack mentioned, led by one of our alumni, Bethany Ellman. Professor Carly Peters, Emeritus at Brown, is also a key player in that mission, building on discoveries of her earlier missions that discovered water at the surface of the moon. So the economics, we think nowadays, are probably more, I think, a bit stronger in that regard. I've been involved with some other kind of private ventures talking about asteroid mining, and the name of the game, the economics there, is water extraction, and primarily water extraction on the moon. Certainly you can use it for human consumption, and that would be vital for a sustained presence, but also primarily for splitting that water to produce hydrogen for fueling spacecraft outside of Earth's gravity well, so you can propel and get to deeper space faster. And then as a byproduct, you also get oxygen for breathing. So there definitely is an economic aspect to it. And I think it'll be really fascinating to see how that plays out with the private sector having an ever increasing footprint in space exploration. But I only see that getting larger, and I think the moon is absolutely central to that.
Yeah, and I think that one of the interesting things on the lunar exploration was they've been naming the astronauts that are being lined up to go to the moon as the Artemis program continues, and one of them is going to be our own astronaut. Woman astronaut that's going to be going.
There are a couple questions about how you actually do this, how you get this thing on the moon, and once there, how you control it. So one question is, what's the scariest part of the 7 minutes of terror? And then another one is, how do you control the drone given the time lag in communicating with it?
I'll talk on the scariest part, Ralph, and then you can talk about controlling. Okay, I'm just going to say the scariest thing is the whole thing. And I remember at the last landing, I was at JPL for that, and talking to some of the engineers, and it came to light. I said, so how do you test something like this? He said, well, we're going to test it tonight because they can't actually do an end-to-end test of the whole thing. They can test the pieces. So that's why I think the whole thing is kind of scary.
Yeah, I was going to say exactly the same thing. I think the whole thing is scary. And so, as I said, I've been extremely fortunate to have been involved in the Curiosity rover since landing day. And I will never forget being at JPL in the room the night it was landing. And I and all of the other, scientists, engineers there are just really nervous. It used the same entry, descent, landing technology as Jack showed in that video for Perseverance. But for Curiosity, of course, that was the very first time this was ever going to be done. And the whole thing to a scientist like me just looks kind of crazy. And the engineers are like, this is going to work. It's perfect. It all makes sense. Okay, that's why we trust the engineers. But in that room, we were all just really, really nervous the entire time. And of course, because of the time lag, it's already happened, and you're only finding out about it several minutes later. So the whole thing is scary. To me, I think the retro rockets and relaying it down on the cable, I think, is perhaps one of the more nerve-wracking aspects when I watch that video and think about it. And then in terms of the communications, that's a great question that comes up a lot. And we actually only uplink commands to the Curiosity rover one time a day, and we kind of have to wait till we're in good alignment so that we can do a direct from Earth to Mars to the rover link, as opposed to relaying everything through our satellites and what have you. Now, so we kind of have this one critical point in the day when we're planning. We have to have the commands all sequenced and done, and they have to get uploaded in this narrow little window of time. And our whole planning day is dictated by that little narrow window. We downlink data maybe 5-6 times a day or so, using orbiters and other assets that we have at Mars in orbit to relay that data through the deep space network, and then ultimately back to JPL and other places.
I see a question in here for Ralph, which is essentially, how did Mount Sharp form?
Well, that's the $2.5 billion question, I think, for the rover. I think, so the answer is, we know part of it because we've explored the bottommost layers of the mountain. And I think this is ultimately what really, and I was one of the lead advocates for going to Gale Crater and exploring Mount Sharp and did research as that to advocate for it. And I will say, we made certain predictions, which makes it a little nerve-wracking then that you actually go there and they can test your predictions. But I think what ultimately solidified that as the site to go was a mountain that tall, and the diversity we saw in the imagery, it must be formed by a number of different processes. It's not just one thing. So we've been marching through ancient lake beds, but we can see in the distance, we're starting to encounter probably thicker units of sandstone. So think Aeolian, dune systems, ancient sand seas. There might even be kind of volcanic materials and sequences in the part higher up in the sequence. So it's not just one thing, it's a number of different processes. And that was really what solidified it as a great choice, I think, because a priori, we don't necessarily know where the best place on Mars or rock type would be to kind of look for organics or habitability and things like this. So the place that has diversity is the best place to go. And we're able to kind of march up through all those things and figure out exactly how it formed, as far as we can drive up, that is.
But I guess, so initially there would have been a lot of sedimentary rocks, and Mount Sharp is the sort of remnant. It's kind of like the towers in Monument Canyon, just Mars versions.
Yeah, so there are a couple different theories out there, but ultimately you're forming a large hole in the ground from the impact process itself. The mountain that we see today is not the actual central peak or ring structure associated with the impact. It formed after the fact from sediment infilling that. Again, some might be volcanic from lava flows or ash deposits, things of this nature. But what we think is happening is at least much of that crater was once filled up with sediment. And what you see today is the erosional remnant of that you've kind of hollowed it out. And people have done experiments in wind tunnels and so forth to show that if you take a crater and fill it up and you blast it with winds, you actually create these katabatic and strong wind patterns that self-feed in itself and gets even stronger. And it will create a kind of dome-like, mountain-like structure like we see in the form of Mount Sharp. But we do believe it, most of it, if not all of it, did once extend to fill the crater and has since been eroded.
Okay, I see a question for Jack in here, which is, can you steer the lander as it's coming down through its 7 minutes? How close can you get to where you want to be?
Yeah, that's interesting. Actually, this Jezreel Crater was proposed as a landing site for the Curiosity mission, but it was taken off the table because it was considered too dangerous. But in that time, technology had been developed to do something called hazard avoidance, and so using terrain relative navigation. So they're using images that they have, that is the rover as it's landing is real time processing those images like military technology does, and they can do just slight shifts. So if they're coming down to land on top of a big pile of rocks, they can move a couple hundred meters out of the way. So you can't really steer it, but because you only got 7 minutes and it's only in that last second, but they do have the capability. And they had to, that was one of the differences when I was on the standing review board for this mission. It was one of the things we spent a lot of time with. If we're going, it costs a lot of money. And so it cost maybe $120 million to develop that technology. That was $120 million that couldn't be used for other things. And so we had to say, is that worth the investment? And yes, that was worth the investment because this target is so great. And we hope by some of the upcoming rovers, we can get the ability to land into something like a 10-meter window as opposed to a 10-kilometer window. So we're hoping to get down to much smaller capabilities.
Yeah, and I think that's just one of the most exciting things about the evolution of Mars exploration. I almost put a slide in there to show, but you can Google it, Mars landing ellipses and how they've shrunk over time, given the new technologies. And I think the great thing about this kind of terrain relative navigation and the radar technology is that that's something that can easily be exported to missions for other places in the solar system where we don't have all of the great knowledge about the surface topography like we do with Mars, where it might, have in the past been much riskier, but with these kind of pinpoint, precision landings, landing things on, say, the surface of Europa in rough icy terrains or things like this, might be much more feasible now compared to, just 10, 20 years ago.
There's one question in here I think is an interesting one, which is essentially how the rise of private launch vehicles and companies like SpaceX is affecting or being integrated into scientific exploration.
Yeah, that is a good one.
What do you see as the future of that, I guess, is a way to ask it, maybe.
Well, it is a good one. And, NASA has actually turned the lunar exploration, part of the lunar exploration, over to a commercial companies to do the delivery. So NASA will no longer be the delivery mechanism to get instruments onto the surface. It's going to be up to the commercial partners. And then there's SpaceX, Elon Musk's company, which completely independent of NASA and the international community wants to land fairly significant payloads on the surface in 2024, maybe 2026. And in that, they have excess capacity. And they said, well, you want to add another a ton of mass. Hey, we're going. You can pay for it, and we will take you. So it will change the equation, I think. It is changing it.
I see we have a Lincoln Field question, maybe adjusting topics a little bit here. So this is asking about, if you think landing on the Mars is complex, just try to envision moving a building that people have inhabited for 50 years. And so the question is essentially, where are people going to go during the Lincoln Field renovation? How are we managing all of that?
So there's Brown puts together, is obviously thinking this through and has developed the concept of swing space. So during the time when we need to be out of the building, something on the order of 12 to 16 months, we're being moved over to parts of Maxey Hall and other places. So it's not perfect. The spaces are rough, but they're spaces, and will still be proximal to our flagship, the Deep's home in McMillan Hall. So So it'll be double disruption, right? Move out, and then we have to move back in, and move out, get settled, and then move back in.
Yeah. Maybe looking ahead even further in time, what are the major challenges for sending humans to Mars?
Yeah, so that's a good one. And as I mentioned, I think you know, one of the critical goals of the Curiosity rover mission that you don't hear much about is this aspect of characterizing and measuring the radiation environment on the surface of Mars. You know, we have our magnetic field to protect us from an awful lot of stuff here on Earth that would otherwise be harmful. Mars does not have a magnetic field anymore. And so there's a lot of radiation that gets sent to the surface. And I think, to me, that's one of the really big things that stands out. You know, I think you know, engineers, scientists are very clever at figuring out ways to squeeze the water out of the rocks on Mars. And on Mars, we know we can map out water in the surface soils and rocks and things like this, and we can extract that. I think the Perseverance rover has instrumentation that's actually going to, MOXIE, that's going to kind of investigate this idea of producing breathable oxygen. But to me, the radiation question is really a big one. Because to shield yourself, you know, if you want to take a lead or something, you could do it, but that's a lot of mass, a lot of weight to carry with you and launch. And I think the radiation question is the biggest one out there. And that's true for the moon and other surfaces as well. But I think we're getting a much better handle on that for Mars based on the data that we've gotten from Curiosity, and with Perseverance actually doing some real experiments about, you know, producing oxygen for breathing. I think these are major steps in that ultimate goal of sending humans to the surface of Mars.
I think maybe I'll ask one final question. I think I'd like to start with Melly on this one. What do you look forward to learning most from Perseverance? Maybe you could each kind of briefly answer that one, but yeah.
Sure. Yeah, I can definitely answer that. So one of the things that I am working on in my research is using one of the instruments that will be on Perseverance Rover landing in Jezreel Crater, which is the instrument called Pixel, the Planetary Instrument for X-ray Lithochemistry. And it makes little rasterized elemental maps of the rocks on Mars in a very small scale. And I'm really hopeful that it's going to help us be able to understand the chemical variations in various sedimentary rocks. So maybe that will help us to unravel some of Mars's ancient history. So that's the thing I'm most excited for.
What about you, Ralph?
Yeah, so I didn't go into the details of it in the interest of time, but what we've established that there was a lake in Gale Crater with the Curiosity rover. The interesting thing about Gale Crater, though, it doesn't have this obvious giant channel flowing into it for the source of that water. So we think a lot of that water was probably groundwater coming up. And Jezreel is fundamentally different. It has a beautiful inlet channel, a beautiful outlet channel. And so, you know, right there, that water was there. It was probably, and you know, some information about the depth of that water. And so it's a fundamentally different kind of lake system. So I'm just really excited to see more about that, learn about the chemistry there and the record, and compare that to Gale Crater, which also had a lake and evidence of a delta, but again, didn't have these channels. It was probably more of a groundwater fed lake system. So very different. So that's one of the things I'm really excited about.
Yeah, both those are awesome, Melly and Ralph's. And what I want to know really soon, as soon as it gets there, is where does this carbonate come from? I showed you that image with all the green colors on it. And this is kind of a fascinating conundrum about what it's doing there. It doesn't really make sense. And so I really want to learn more about what it's doing there, what it's associated with, and what it tells us about the climate and habitability, and get some samples and bring them home. That's what I want.
Okay, I think that pretty much wraps up all of the questions. If there aren't any more questions, I guess I'd like to close by saying that we're all really looking forward to learning about what Perseverance has to tell us about Mars and the great discoveries that are going to come from the Planetary group at Brown. Really looking forward to seeing what the new Lincoln Field building looks like. And I'd like to thank everybody who attended today. If you're interested in getting involved and learning more, feel free to reach out and contact me. Or you can reach out to Catherine Nellis to learn more about how to get involved in planetary science and other activities at Brown University.
Thanks so much, everybody.
Yes, thank you so much for joining us. And,
Thank you.
tune in on Thursday.
3:43 p.m. Eastern Time.
There we go. I put just so everyone knows, I put a link to a website, NASA website with a countdown, so you can actually, look at it with bated breath and monitor the seconds. Thanks again, everybody.